Welcome back, everyone. This is a demo on the class project that I did, and I presented earlier on the earlier video. The Perry-Mason annotation. I will walk through some of the codes that I used and some of the test runs to so that the code actually works. So here I am connected to my lab desktop just to show you that to show a few couple of runs of the training session related with my laptop is slower than desktop, so I tend to use the desktop from the lab for the demo. But I'll walk you through the code here. Here is the code that I have used, all the codes that I have used. For the first part of the code, what I have is um, let's see. Let me show you training data that I have used. So basically, my training data with the annotation ground truth looks looks like this. This is the overall paths that I have used, and the goal is to get the annotation, all these black paths automatically done. And this has been manually labeled by myself for the for to train the convolutional neural network. Out of this, I create a ground truth mask out of which I sample the positive and negative pixels and then crop a patch of smaller size 32 by 32 or the multiscale patches centered on that pixel. So these the pixels on this area form the positive samples, whereas this forms the negative samples for my implementation. Yeah, I have already, since creating the patches and everything takes time, I have already created some of these square patches and stored them in a mat file like this. Uh, it basically stores a data structure that I have. Let me show you some of the couple of examples. So the training Training data structure basically stores the data information. So the number of samples that I have, width and height, and then the number of channels, and the label of each of the data like this, and the actual data, RGB values of the data in the four-dimensional array that has it's basically the structure that the code that I'm using supports. Similarly, I have a for the testing phase, what I have is a ground truth that I already created out of the ground truth annotation that I did. So my positive ground truth mask looks like this. This is basically a binary mask. This is the region of the perimeter, which are the pixels that I use as the positive samples, and this is the negative mask that I use to create a negative samples as well as later on to do the evaluations. And this has been created using create mask code that I have here. So it basically reads the mask and the files, and then basically creates the smaller patches and it stores them as a mat file, like I already showed you for the training data as well as for the testing data. Get features is just to get the smaller batches of data, and also to create the LBP features, local binary features. Since for the convolutional neural network I'm using raw uh, uh, RGB values, I don't need to create the features. And there are a few other codes related, like to read the directories, to plot the precision recall, which I downloaded online, to get the statistics of the overall performance, and also to get the average precision that I have included, that I will be submitting on the class websites. And there is also a evaluation run code that basically computes all the precision recall and phonics score for all these three cases. Let me walk you through the training code first, and then maybe just show you a sample that the code runs. So going back to my desktop, the convolutional neural network code has been downloaded online. I will put the source when I submit the code. Just to show you a couple of epoch of training. This is the training architecture code that I have written myself. This is the layer. This is the part where I define the architecture that I have used for my convolutional neural network. The architecture that I described on the previous presentation here. This is the part where I'm just reading all the batch of files that I have, like these smaller batches. I'm reading them and compiling them into putting them into the memory to form a single bulk. I'm subtracting mean and dividing it by standard deviation to normalize it, and then organizing the validation test data in the similar way. The weights has been randomly initialized here, and I run my training for 50 POC. But as I said, to avoid the overfeeding, I decay my weight and then I stop it as the performance does not improve further on the validation data sets. So this is the overall testing code. Let me just show you that this code runs. Just quick run. I will not run through the whole because I already have a trained model. By the time the code runs, I'll show you the trained model on my cell is saved on my laptop. As you can see here that I stopped at the 40 POC and the validation error is around 82%. I mean the 18%, and the weights that I'll be using now for the testing looks something like this. So this is the overall weights for all the hidden units in the neural network related to convolutional network or the max pooling layers. As you can see on the demo that my training is running on each batch, it's running the first POC. I'll stop this code here because I don't want to run this the whole through the whole data set. It takes almost around 8 hours to go through the whole epoch and the whole training data set, just to show you that this code runs. Okay. Now for the testing part, I have a code called CNN segmentation. What it does is basically reads the whole image, the testing data set. Sorry, to turn it on the testing images, and runs the sliding window on each image uh, to get a probability map and also the overlaid image. I'll also show you the run on the segmentation code here. Just yeah, this is how my testing image looks like if it expands. Basically, yeah, this is my testing image and I'm running. This is the image after normalization and this is before normalization, and now I'm just running the convolutional neural network model on each pixel on this image. As you can see, the code is running, so I will just stop it here and I'll show you the final results that I get out of after training the after doing the run. So here are some of the results. So this is the overlaid result after running the convolutional network. And this is the binary mask that is output of after threshold, and this is the probability map straight out of the convolutional neural network. So as I already mentioned that I ignore the boundary pixels, which you can see to be black here. So this is the overall output of my implementation. To explain the code further, I don't think there is much here. So this particular code here is just to run a matrix to plot a ROC curve, which I included in my report. Go back, yeah. I'll be including all this in a code in G code once I submit the. I'll put all the code in a G file. I'm sorry, I don't know what's going on with me today. I'll be submitting all the codes in a zip file. I'll submit my report and everything. Let me see if I need to explain any other code. So this is the budgeted SVM or the large scale SVM code that I used. I don't think I'll be putting it on the code package. I'll be surely posting it the online source where I downloaded it from. This is the LBP features calculation code that I downloaded from online. Oh yeah, there is also the evaluation code that I have. So what basically this does is, right, when I run the evaluation, let me show you one sample of running the evaluation. Yeah, so once I run the evaluation, so for this particular part, I'm running the evaluation on the neural network, and the output on the all the training data sets. So there are 17 training data set that I used, and this is precision, recall, and the F1 score on each one of them. There are a bunch of other metrics that I computed, but I haven't included them on the report. They are not really significant. And the get stats on the and the other code, they compute the average and the standard deviation and everything of the precision recall and the F1 score. There is also a precision recall plotting curve, uh, and this is the part where I get compute the precision recall for each image in the testing sets. My testing images are stored here, and their respective ground truth are stored here. The model that I need for to do the training is stored here, and also all the test images, also all the results that are computed by different methods are stored as such. I'll not be including all the results and everything since this data is not public, but from the video, you can see that my code works, and these are all the code that I use for my project. Thank you for listening to me, taking your time out to listen to me, and um, as you can see, my results are pretty decent and pretty good, not decent, and they are remarkable. So I plan to publish, do a publication on this on some area. Thank you for teaching this class, and I learned a lot. Thank you.